Hi, everybody. Dr. White here. I want to talk a little bit about the section on further applications of integrals, where you look at volume, density, and average value. We're going to focus on volumes in our work. We might come back to this some other time and maybe pick up things like average value or density if we see a need. So just read the bit on volumes in the textbook. Just looking at the textbook initially, if you want to find the volume, if the figure is simple, it's not too hard. Like this figure here is basically the same like kidney shape all the way up, okay? And anything that has the same shape all the way up vertically is called a right cylinder, even if the base shape is complicated like this instead of being a circle, okay? So how would you get the area? You would just take the area of the base, whatever that is, times the height, and that would be the area for the whole curve. The question is, like, what happens, how do you work it if the figure doesn't have the exact same congruent cross-section all the way up? What if the cross-section changes on you? And the book suggests a way of looking at it using little Riemann sum-like things involving little slices that are very thin. Okay, and so we're going to do something similar but a little bit less formal. We will apply it though to this problem right here, because then I can refer you back to better pictures in the book than what I can draw by hand. What we want to do is to get the volume of this pyramid here, okay? And that pyramid has a base that is a square that's 4 meters on each side. And so down here at the bottom is a square that's 4 on each side, okay? And its height is 12 meters, right from the center of the square on the bottom all the way up to that point, that vertex point C at the top is 12 meters. And so if you were to cut that pyramid in the horizontal direction at different height levels, you would get a square each time, but it would be a different size square each time. These would not be congruent squares. So how can you get the volume? Well, the idea is if each of these squares is like a really, really thin sheet, and it's at some height y, and so think of its thickness as dy, if you could find its area, then multiply that by the dy, you'd have the volume of that thin little sheet, and then you could add up the sheet volumes all the way from the y equals 0 level, which is the base square, to the y equals 12 level, where the square has shrunk to nothing, okay? And that would give you the total volume. That's going to be our idea. So I'm going to head to our notes and let's see if we can work this out. So I need to think about that, that pyramid. And so it's going to be helpful if you just look at some triangles that are associated with one of these little horizontal slices. Let me head back here just very briefly. Do you see how they are drawing here a triangle that like starts at this point where I'm waving my mouse, goes right through the center B point over to the A point, up to the C, and then down back to this point again? That would be some little isosceles triangle. Well, I'm just going to focus on half of it, from the B up to the C, down, and then over to the B again. Okay, I'm going to focus on that, and I'm going to focus on that Y level here. And I'm just going to draw that stuff in my notes. And you'll find yourself doing a lot of the same thing, taking a little 2D piece out of a bigger 3D picture. So here's my triangle. This is the B point here at the origin on the XY plane. This is the C point up here at level 12 on the Y-axis. And then this is the edge of that triangle that we looked at over at 2 on the y-axis. Why 2? Because the square is 4 wide. So from the center out to the side of the square is 2. And the y level, this little horizontal strip here, that's from the center of the square at the y level out to that right-hand side. Okay? So it's not, you're not looking at a piece of the whole square. There's another piece that would go out this way, and then you're only looking at, like one little vertical line within the square. But I'm very interested in this piece here because that piece would be half of how long each side of the square is. Again, check back and you will see. So the whole square, they're calling S. Okay, the side of the whole square, they're calling S. And so here's an S. Here's an S. Here's an S in back. Here's an S coming over there. But from this point out to this side, which is what I've drawn for you, that would be half of S. Okay? So I'm very interested in this because it's half of S, and I would like to know S. S is the side of the square that makes the cross section at height y. If I can find half of S, I can find S. It'd be great. Well, how can I find half of S? When I look at this stuff here, I see two right triangles. I see a smaller right triangle here, and I see a bigger right triangle here. And they are similar right triangles because they're both got a 90-degree angle, and they both share this angle up here at the top. And so all three of their angles are the same, and so they're similar triangles. So I can use that. If I label things well, I can use the similarity of those two triangles. So let's think about it. Let's draw the same thing, but without the axes to distract us. The big triangle would have a height of 12, okay? But that's broken up into the y level and the rest, which would be 12 minus y. The big triangle is 2 on the bottom. Now the small triangle that ends down at the y level is s over 2 at the bottom. And so I can think by similarity of those two triangles, vertical side short triangle divided by vertical side of big triangle is bottom side of short divided by bottom side of big. So just ratios of corresponding sides have to be the same. And so I get an equation for S in terms of the y level. And I gradually solve it, and I get that S is 12 minus y over 3. So what I've learned is that at height y, that cross-section that you saw earlier, that little S by S cross-sectional square, is a 12 minus y over 3 by 12 minus y over 3 square. And it has a tiny thickness dy. And so its volume, which I call dV, because it's an infinitely thin volume of a little infinitely thin sheet, would be 12 minus y squared, side, times dy. So how would I get the volume of the whole pyramid? I would just need to add up the dVs for all of the squares from height y equals 0 up to height y equals 12. That's this integral here. And so I do what I can. I square the top and the bottom, and I get a 1/9 that I can pull outside. And I look at this, and there's various things I could do. I'm going to just do substitution. U is 12 minus y. Eventually, I find that dy is minus du. I'm going to need to change my limits. And I think, well, when y is 0, then u, which is 12 minus y, would be 12. But when y is 12, u would be 12 minus 12, which is 0. And so when I do my substitution, I end up with this. I take the minus outside. And, the integral from 0 to 12 could be better thought as minus the integral from 12 to 0 is better thought of as the opposite of the integral from 0 to 12. So I do that. And now I've got a plus 1/9, this integral, which we've done the likes of before. So antiderivative is u cubed over 3. So I've got 1/9 of that is a u cubed over 27. Evaluate between 0 and 12. Plug in my numbers. Here I am kind of like simplifying. I found that you can cancel a 3 cubed from the top and the bottom. And I get 64 meters cubed is the volume. Great. Just a couple of notes about this. Y'all might have looked at this integral and said, can I get the antiderivative without all that work of substitution? And you probably could. It's totally fine to do like a guess and check, where you kind of like guess, maybe the antiderivative of this is 12 minus y cubed. And then take the derivative of 12 minus y cubed. And just see how badly you're off. And you're off by a factor of -3. And so compensate for that. Multiply your original guess by -1/3. And then you'll see that things work out. And so you end up, then you would just do this for your further calculations, and you would get the same results. I think the book they say they're doing substitution, but they kind of mix in, they use these limits here. The second thing I want to note is just a general idea for finding volumes of solids using cross-sections like this. So, if you've got some bizarre solid that can be thought of as cross-sections from a low height y equals a to a big height y equals b, so like here's some arbitrary cross-section at some height y between those two, just find that cross-sectional area some way, get a formula for that area in terms of the height y. And so how you do that's going to vary depending on your setup. You could be using some simple geometry and similar triangles or other geometric facts or facts about areas of types of regions that you know about, but you'll find it, a of y, multiplied by the thickness dy, and you'll have your little volume. And then if you add up all those little volumes like we did, you'd have the volume of the entire solid. And so that's the main idea for finding volumes using these cross sections. Add up the little volumes of the sheets, but you got to get a formula for the cross-sectional area of the sheet. Let me try another example. How about volume of a sphere? Okay, and so like not the circle that you see here, but a sphere. And so I'm actually working on another problem in the book down here because they draw a prettier picture. Imagine that sphere you see. So that sphere is solid. It's coming out of the page at you, and it's also going back in behind the page. But there's the XY plane that's the page itself. And so the sphere intersects the XY plane at a circle that we'll look at rather closely. Now, say the sphere has a radius of capital R. What's its volume? It turns out the volume of a sphere whose radius is capital R is 4/3 pi r squared. See where I'm waving my mouse? And I'd like to give a little bit more detail about how they're getting that. So their idea is this. They're going to let x vary from -r to r. Okay, so here's like an arbitrary x between those two values. And they're going to draw from the x-axis up to where you hit that circle that's in the xy plane. And you just rotate that around, just rotate the line around, you would get one of the cross sections of this sphere. So each cross section is a little circle that's going like right up out at you and right back into behind the page. Okay. And you're just going to get the area of each of those circles, and you're going to multiply there by the infinitely small thickness dx and add those up. Okay. So to get some more detail on that, let's head back to the notes written up here. So here's that circle in the xy plane, okay, -r to r on the x-axis. Arbitrary x right here. And so I am looking to go up to the circle, because that vertical distance there, that's actually the radius of the cross-sectional circle, okay? And if I know the radius of a circle, I can get its area. So I'm going to want to know about that y. Now what I notice is in the right triangle right here, the hypotenuse has to be capital R, because from the center to any point on the edge of the sphere has to be its radius, capital R. And the horizontal leg is x, the vertical leg is y, x squared plus y squared is r squared. No surprise, that's the equation for the, for a circle in the xy plane that's centered at the origin. So that y that I'm looking at there is the plus square root of r squared minus x squared, okay? And as I point out here, again, that's the radius of the cross section whose area we're trying to find. So since the thickness is dx, to get the volume, we're going to add up from minus r to r all of the little volumes, which are the cross-sectional area, times dx. This time the cross-sectional area is expressed in terms of x. It's pi times the radius of that circle squared. You got to express that radius in terms of x. That's why I did y is square root of r squared minus x squared. So we are now ready to just take this integral. Squaring a square root gives us a simpler thing to look at. The pi is a constant. It can come outside and you can get the antiderivative of r squared minus x squared. The constant r squared times x minus x cubed over 3. Evaluate from minus r to r. Do some math, and in just a couple of steps, you're going to get that 4/3 pi r cubed. It's pretty neat. Okay, let me just see if I want to go any further. I think I'll just do one more example here before I end this particular screencast. This is also found in the book. It's example 2 in the book. So what they've got here is this solid that they're drawing for you. And the way they make the solid is they've got a parabola in the xy plane whose equation is y equals 4 minus x squared. Okay, so y-axis here, x-axis here, and the parabola is, opening down in the xy plane. And the solid comes up from the xy plane. And vertical cross sections, they say, always look like semicircles. Okay? Could we find that volume? So clearly we're going to have a closer look at that base of the solid. And we'll also want to look at the little line segment that is the bottom of the cross section, the bottom of the semicircle. So back to the notes, here I've drawn y equals 4 minus x squared, this parabola. And you think of the volume, the solid, as coming up out of the page towards you. And you think of cutting right along here, this horizontal level, some level y. And so when you cut, you've got a semicircle coming up towards you. And you can tell that is going to be a radius for that semicircle. So I'm going to want to find that. Well, I can find this by subtracting the rightmost x-coordinate from the leftmost x-coordinate. What's the rightmost x-coordinate? Well, I'm on the curve y is 4 minus x squared, so I solve for x, and I get x is plus or minus square root of 4 minus y. This x-coordinate must be the plus square root, and this other x-coordinate way back here must have been the minus square root. And so if I were to subtract big x-coordinate minus small, then I would just get square root of 4 minus y minus 0. So the radius of this semicircle cross-section is square root of 4 minus y. So what's the volume of the little cross-sectional sheet? Its area of semicircle. Well, that would be 1/2 pi r squared. So it's this, times the little thickness dy. And so I just got to add that up from the y equals 0 height, this big semicircle here, to the y is 4 height where the semicircle has vanished. And so I do it. Squaring a square root gives me an easier antiderivative to think about. But actually, I'm just going to look at that definite integral here and notice that that is this familiar shaded area. It's the area of a triangle whose base and height are 4. And so I've got my constant pi over 2 that was sitting around, but then here's 1/2 base height. Works out to 4 pi, which is kind of neat. One thing I want to point out before we end is Cavalieri's principle. Solids with equal cross-sectional areas will have equal volume. What do they mean by that? Let's head to the textbook again and just take a look at their illustration. So look at this stack of coins on the left. The coins are stacked perfectly on top of each other. You've got a right cylinder there. The area of that cylinder would be the area of the face of any one of those coins times the height. Now, suppose that you just took the coins and you jiggled them around a little bit like they're showing. That would not change the volume of the solid, right? The solids look very different, but their corresponding cross-sectional areas are the same because all that you've done is jiggled them to the left and the right. You haven't changed their shape, therefore it couldn't possibly have changed their area. So solids with equal cross-sectional areas as you go up have the same volume. So this is useful sometimes. Let's look at, I'd say to look at number 23 in the textbook. So let's head down to the exercises. Let's see if we can get to them. Yada, 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 yada. 23. Here we go. Take a look at that figure. Do you have to work too hard to get its volume? It looks like it's like a slanted cylinder. It's not a right cylinder. And they give you like all this information about how much it's slanted. But really, if you just think of it as like the coins, it's basically like somebody just moved the coins over kind of in a regular way. If you just switched the coins back, stuck them all exactly on top of each other, you would have a right cylinder whose base is, I'll just go back to the notes, whatever they say the base is, whatever radius they give, and its height was 10. I think they said the radius was 4. So the volume would be the height, 10, times pi times 4 squared. So that's like, what, 160 pi cubic units. So don't forget Cavalieri's principle that can simplify the finding of volumes for you in some restricted cases. I'd like to do another example, but I don't think I really have time for it to give it the right now to give it the detail that you probably like. So I'll do that in another screencast soon. Let me see if I can find out how to get out of here. Okay, bye-bye.